So in this example, we've got an overall reaction of A plus B to make C plus D. And it occurs via a two-step mechanism where step one has A at equilibrium with Q. You don't have to know much about equilibrium at this point, but you'll notice the arrows point both forward and backwards. What this means is that A is forming Q and Q is forming A at the same time, at the same rate. So as an A turns into a Q, there's a Q turning into an A, and this is happening relatively fast in the mechanism. Step two, we have that Q reacting with B to make C plus D, and this is our slow step, or our rate determining step. If we were to try and write our reaction mechanism, or our rate law, if we were to try and write our rate law based off the slow step of this mechanism, you would write that rate equals K times the concentration of Q to the first power, because it has a coefficient of 1, times the concentration of B, also to the first power, because it has a coefficient of 1, and that would look like your rate law. But since Q is an intermediate in this reaction mechanism, and you can see it's an intermediate because it's formed in step 1, but then consumed in step 2, since Q is an intermediate, we can't leave it in the rate law. But luckily, since step 1 has A being at equilibrium with Q, they're interchangeable within that rate law. So whatever Q is at equilibrium with, since it's the intermediate, has to be replaced by whatever it's at equilibrium with, which is A in this case. So this rate law would read rate equals K times the concentration of A rather than the concentration of Q, because again, Q is the intermediate, it can't appear in the rate law. And B is just fine to leave because it's just actually a reactant. And they're both to the first power because both coefficients of A and B are 1. So that would be our rate law for this reaction.